Okay, I think we live. Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and college or university levels. And if you're interested in getting some help with your homework or if you're interested in tutoring, please check out the links in the description below. Cool. So let's get this show on the road and let's experience some physics. So I'm going to switch over my screen real fast and we can get this party started. Okay, so let's get it moving. Cool. So this is the first question that we got on the menu today, and this question is asking us, since velocity is equal to the wavelength times the frequency, that is a universal wave equation, by the way, does the speed of the wave depend on its wavelength? And the short answer is no, but we can take this a little bit deeper here. Okay, so imagine for the universal wave equation, it's V equals lambda f, lambda being wavelength, f being the frequency. So imagine that we have a wave like this. If we wanted to change the wavelength, like shorten wavelength, it would look something more like this. So this would be our lambda previously, and this will be our lambda now. So also keep in mind what happens when we shorten the frequency, when we shorten the wavelength. We're also going to increase the frequency. Well, that's kind of what needs to happen, because you see how the wavelength is shorter, means there's less time between each like peak of the wave, and the time between the peak and the time between peaks, that is the period, and 1 divided by the period is the frequency, 1 over t. So shortening wavelength also increases frequency, and they're like highly connected that way, provided that they are occurring in the same medium. Shorten wavelength in the same medium. Okay, so a shorter wavelength corresponds to a shorter period, and a shorter period, which is t. Why does period is represented with t, even though there's no letter t inside the word period, and that's just kind of the way that it is. But when we increase the period, when we decrease the period, we increase the frequency. Okay, so wavelength and frequency are directly connected to each other typically, but v, the velocity, speed of the wave, v, this depends on the medium that the wave is traveling through. Depends only on the medium that the wave travels through. Okay, so yeah, it's not dependent on the wavelength. A wavelength depends on the frequency, but the speed depends on the medium. Some examples would be like speed of light in vacuum. A light in vacuum is going to be 3.00 times 10 to the 8 meters per second. that's one example of like a speed value that you might have for v. Another example could be something like speed of sound is going to be approximately like 330 so meters per second. So this is just some examples of some different speeds of waves that you might do. Like the speed of sound, of course, is like even a different type of wave. So it depends on the medium as well as the type. But the type of the wave is also kind of associated with the medium. Yeah. So I guess it's fair to say that it depends only on the medium, which also includes the type of the wave. So yeah, the above solution is good. Above solution is good. Cool. Fun stuff. Okay. So the next question that we got on the menu today is asking us, how do we find the period of a wave? So let's actually define the word period in terms of waves in a more concrete sense. Okay, so a wave period is the time it takes for one wave cycle to complete. You could do like time between peaks. Can measure as time between peaks. Okay, so suppose that we have a graph or a wave that looks a little something like this. So here we have our, let's just say W for wave, and then along here we have time. So suppose that we have maybe a sinusoidal looking wave, looks something like this, and of course it's going to repeat and repeat and repeat. So what you could say do here is, you see this would be one wave cycle. One wave cycle. This could be maybe T2 and this could be T1. Period. T could be equal to T equals T2 minus T1. And of course, like T1 would be 0 in this case, but we don't necessarily need T1 to be 0. Maybe I can put this in another color. Like if we wanted to do the distance between the peaks, wait, that should line up with the, just pretend that's a straight line. If we do the distance between peaks, this could be like maybe TA and TB. And the time difference between them should also be T as well. So it doesn't matter where on the wave that you're taking the measurement for period. It just matters that, you know, you have an entire wave cycle between your time measurements. Typically, people will recommend that you use the wave peaks because they're very visible and they're not at all ambiguous on where they stand. If you do like in the middle of the wave, maybe somewhere here, it's going to be tough to know exactly where. Like it's going to probably be within there, but to know exactly where is going to be kind of tough. So you typically want to choose an easy point where you can easily and clearly, unambiguously identify when you see it again on its subsequent wave period or wave cycle. Okay, so yeah, they have this example here. So you see this is, I guess I use the same sinusoidal function as an example. And you can see that as soon as it repeats, that will be your T point, which is like the time of one period. Okay, and So this would be how you do it visually by looking at a graph. But sometimes you'll get a wave equation that's a little something like this. So scrolling down here, let's go back to a black color pen. A lot of the times wave equations will come like this. You might have something like your signal, let's call it y, kind of like they do here. Y could be equal to a sine your angular frequency, omega t. Generally you want to use omega for angular frequency, and we're doing this all in radians, plus some phase constant. You might also see it as a cosine as well. Not as common, but cosine is commonly seen as well, but it's less popular than sine. People like sine. I'm sure there are some signs as to why that might be the case. But yeah, so we want to extract the angular frequency and we know that angular frequency is equal to 2 pi frequency, and we know that we can isolate for frequency by doing f equals omega divided by 2 pi, and we know that this is equal to 1 over t, because frequency is the reciprocal of the period. So we can use this equation and we can keep it moving to isolate for t. So t is equal to 2 pi divided by the angular frequency. Okay, now I'm not sure why they use p for angular frequency. Could be a formatting thing, but this would be how you find the period of a wave if you are given its equation. But if you're given it visually, just identify where the wave starts, where the wave ends, and look for the distance or the time between them, and that will be your period. So yeah, the above solution here is good. Is good. Unclear as to why p was used to represent angular frequency instead of omega. Okay, cool. Okay, so the next question that we got on the menu today is asking us, what is the value of arcsine of 1/2? Okay, so arcsine, some of you may have seen arcsine already, but in a different format. So arcsine of 1/2 is equal to sine inverse of 1/2. Now the reason why you might use arcsine instead of saying sine inverse is because sine inverse can sometimes be confused for sine 1 over 2, but this in to the power of -1. These are not equal. So this is an inverse operation. This is equal to 1 over sine x, or sine 1/2. That's a reciprocal. Okay, so that's why we might use arcsine in the first place, because inverse sine can sometimes be confused with reciprocal sine, especially considering that this case is... so this is confusing because you see stuff like this. Sine squared of x is equal to sine x squared. So because we use this, it can be quite confusing when we see inverse sine this way, because we've seen this. So we use Arcsin to be like concrete about it. And let's actually think back to SOHCAHTOA and imagine that we have a right angle triangle. I'll draw one right here with the power of Microsoft Paint. So suppose that we have a couple, well, what do we know about this? Well, we know that here we have the hypotenuse, the hype. If we have this as our angle theta, this will be our adjacent, ADJ, and this will be our opposite. Now, sine theta, as we know, is for the SOHCAHTOA is opposite and hypotenuse. So sine theta is going to be the opposite divided by the hypotenuse. Okay, and if we wanted to get the theta angle, well, we would use this inverse sign. So if we do this, theta equals sine inverse of op over adjacent, and you know, this is the same as saying arcsine. Op over adjacent. Okay, kind of see how that works. Cool. So let's actually sub in our value here. We have 1/2. So basically we're trying to solve for, I'll write it as arcsine 1/2. So we know that extracting from here, our opposite is equal to 1. Our adjacent, no, not our adjacent, our hypotenuse is equal to 2. Now, the only configuration that this would be possible is if we have an angle of 30 degrees. And you can actually, like, this would be something that you would really want to type inside of your calculator. But where this comes from is, like, assuming that we have an opposite length of 1, and this length is 2, and we have a right angle here. Consider this, okay? If we just drew a reflected version of it, that would be 1. This would be an equilateral triangle. This would be, that would be 1, and that would be 2. So overall, this would be 2, and this angle overall would be 60. But it would actually be 30 and 30. So I'll write that in red. 30 degrees, 30 degrees. So you can see that if the opposite is 1 and the hypotenuse is 2, it has to be 30 degrees. There's no other option of how this could work out. Okay, so another way that you could write 30 degrees is 30 degrees equals arcsine of 1/2. Another way that you could write this is pi over 6, and that's just the radians version of it. Okay, and gradients, don't worry about too much about gradients. That's fairly rare that you'll ever see it. But yeah, so it really is just taking the arcsine, and you can see that, yep, they got 30 degrees and pi over 6, and that would be precisely what the result is of the arcsine. And hopefully from the diagrams here, we can see why this works out, where that comes from, and then we can be happy that we are mathemagicians. Cool. So that's going to be, the above solution is good. It's good. Okay, so the next question that we have on the menu today is asking us, what is the atomic mass of an atom that has 6 protons, 6 neutrons, and 6 electrons? So 6, let's write that out. 6 protons, 6 electrons, and 6 neutrons. Now, for the chemistry type people in the crowd, we can see that this is a carbon-12. or this is carbon. It has to be carbon because 6 protons. I'm going to check my periodic table real fast. Yep, that's carbon. Got a new poster of it. It's pretty cool. It's definitely carbon. 6 protons, 6 electrons, and 6 neutrons. Now, when we think about atomic mass, it is the number of protons plus the number of neutrons. Neutrons. Okay, in this case, our number of protons, that is 6. Our number of neutrons, that is also 6. So our atomic mass is 12. Okay, now why don't we care about the electrons? Why is electrons feeling left out of this equation? Now the reason why is because electrons are very, very, very small compared to the mass of a neutron or a proton. So the mass of a proton is 1.67 times 10 to the negative 27 kilograms. Fairly light, and the mass of a neutron, this is about equal to neutron mass. And the mass of an electron is, I believe it is 9. Let's actually Google that real fast because we got the power of the internet. Mass of electron. I think it's 9.11 times 10 to the negative 31. Oh wow, would you look at that? 9.11 times 10 to the negative 31 kilograms. That's the mass of an electron. That's quite light, but if we look at the orders of magnitude, we can see that the mass of an electron is like 4 orders of magnitude smaller than the mass of a proton. Okay, so if we wanted to see how many times bigger a proton is than an electron, if we did like 1.67 times 10 to the negative 27 kilograms divide by 9.11 times 10 to the negative 31 kilograms. Put that in our calculator. 7 times 10 to the power 27 divide by 9.11 times 10 to the power of negative 31, and oops, let me just change something real fast. Forgot the negative in one of my calculator calculations. That is not great, but we got it now. And this is about 1833. Just about equal. So that means that protons are 1,833 times more massive than electrons. That could be like comparing the mass of a grape to the mass of a truck. Like, you know, should we worry about the mass of the truck if we add in like 5 extra grapes into the back of it? Not really, because the mass of a grape is so insignificant compared to the mass of the truck. Kind of like how the mass of an electron is so insignificant compared to the mass of a proton. It's not even worth keeping track of in terms of atomic mass. And a lot of the times, as you'll see more in your chemistry classes, you'll see that electrons don't even stay around that much anyways. So electrons move around a lot. So yeah, the above answer is good. Is good, but could be better, with mention of how protons and neutrons are 18 100 times more massive than electrons, which is why electrons are ignored in atomic mass calculations. Okay, cool. Okay, so the next question that we got on the menu today is asking us, does a particle that moves around a circle at a constant speed experience an acceleration? The short answer, absolutely yes. But the long answer, well, let's actually draw some diagrams and kind of like show experimentally or through drawings what would be going on and why this is the case. Okay, so suppose that we have a circular path that looks like this. Nice and circular, and we got a particle that's looking like this that travels in a circular path. Like right here, its velocity would be this way, and it follows that circular path. It really is going round and round, kind of similar to, like, imagine you're driving a car inside a roundabout. This would be like a similar situation. Okay, now let's define acceleration. Acceleration is change in velocity with respect to time. And let's specify that these are vectors. So changing velocity with respect to time, we can also say that both or either the magnitude and direction can be changed. Okay, what that means is, you know, we typically think of acceleration in terms of like linear acceleration. Like, you know, when you're driving, you hit the gas pedal, that causes an acceleration because you move forward faster. But every time that you make a turn while also maintaining your speed, you have to be accelerating towards the center. So the velocity is going to be changing. So at this point in the loop, the velocity might be looking like this. When you're down here in the loop, your velocity might look like this. Over here, your velocity might look a little something like this. So your velocity is always like curving towards the center of the circle, really. And what's causing that is an acceleration. There has to be an acceleration going inwards. So typically it's called the centripetal acceleration, AC. Centripetal acceleration. Curves velocity towards the center of the circle and stops the particle from just continuing in a straight tangential line. Prevents the particle from continuing in a straight tangential line. Okay, so that's the acceleration that a particle will experience when traveling around a circle at a constant speed. Okay, and the equation for centripetal acceleration is velocity squared. So AC is equal to velocity squared over r. R, of course, is the radius of the circle. And associated with every acceleration, there's typically a force. So we just multiply this by mass to get the centripetal force that keeps it inwards. Okay, and yeah, so the above solution is good. Yeah, and centripetal acceleration is always perpendicular to the angle, or is always perpendicular to the velocity. Okay, that's a good thing to note, and you'll see that more the more you see like dynamics and motions across curves. So the above solution is good. Cool. Ain't that a beautiful thing? Okay, the next question that we got on the menu today is asking us, if we're walking on a highway, what should we do? Hopefully, we're walking on a highway. In general, try not to walk on highways, but if you are in a situation where you have to walk on the highway, I'm going to assume like which of the following options is the best to avoid possible problems that could happen when you're walking on a highway, like getting hit by a car. So the first option is walk on the right side so that approaching cars can see you better. So I mean, if this is our road and it's like a dotted line, or maybe like a semi-dotted line. So if you're walking here on the right side, you can be hit in the back, and because how do you know that cars are going to actually, like, they can see you probably from far away, but when they see you, that doesn't mean that they're not going to hit you. And if you're walking, you're not even seeing these cars as they're approaching you, so they could hit you in the back, because just because a car sees you doesn't mean they're not going to hit you. Sometimes cars see you and still hit you. So it's best not to walk on the right side of the road, even though, right of way, as the old saying goes. The next option is walk on the side with the highest amount of traffic. Now, more traffic means more potential for things, more moving parts, more likely that one of those moving parts could hit you, perhaps. But one possible benefit of the side with more traffic is that in traffic, cars move slowly, so even if you do get hit, it's not going to be as bad to get hit by a slow moving car versus a fast moving car that could be on a high traffic or on a low traffic area. But traffic is not necessarily a great option. And the next option is walk on the side of the road that has the widest shoulders. Now the widest shoulder, like this would be the shoulder of the road. This would be the road. And the shoulder is like it's like this area. It's pretty good, but just having a big shoulder does not mean that cars are not necessarily going to drive there. Like if you're on the right side of the road and on the right shoulder, you can still get hit in the back, possibly by a car that doesn't know how to steer. And you can't always trust other people on the road. It's kind of a cruel world, but it is what it is. So just having wide shoulders just is not great. Like it does help with safety, like stay as far away from the road on the shoulder as possible, but that's not necessarily the best option. In a kind of counterintuitive sense, the best option is kind of to walk on the left side of the road, hopefully not on the road, but if you're here, you can see all incoming cars. So if that's a car, skirt, vroom vroom, very fast, and if it's approaching you, you can see it coming. And if you see it coming, you can personally do something about it to avoid getting hit. So if you see a car is coming and it's kind of like zigzagging on the road as a wild person might do, you can run off real fast perpendicular to the road, and you can really reduce the likelihood that you'll get hit, as opposed to if you're walking on the right side of the road, you'd have no idea if cars are approaching or not unless you're actually turning around, unless you're walking backwards. So it's better to be on the left side of the road so that you can see the cars coming and they're not going to hit you in the back. No one's going to hit you in the back because there's no one going this way. Nobody goes this way. Okay, so never get hit in the back, only get hit in the front, but when you get hit in the front, you can at least see them coming, and at least you had an opportunity to change the way that you're walking to make it so that you don't get hit in the face with a car. Okay, yep, the above solution is good, but has a typo. Would also be good to explain why the other options might be undesirable, or why the other options are undesirable. Okay, cool. So the next question that we got on the menu today is asking us, what is the period of a wave? Period of a wave. It is represented with letter T. With T, which is equal to the reciprocal of the frequency. So that's frequency. And the period of a wave is what it represents is the time for one wave cycle to occur. Okay, so that's what the period of a wave is. So let's actually see some examples of like how we could like visualize a wave. So suppose that we have a triangle wave like this, or a sawtooth wave. If you're into music production, you'll kind of know what this sounds like. It kind of sounds like a buzz. So a sawtooth wave example. So you see how it's like a repeating sawtooth. Like it goes up in a straight line and then straight down and then goes up and then straight down. So that would be like one wave cycle is going to be one, slowly up and then straight down section. So the time it takes for this to happen takes for one of these wave cycles to occur is period, aka T, capital T. Make sure that you remember it's capital. And that's just one example, like a sawtooth wave. Of course, you could do it with like sine waves, or if you have triangle waves or square waves. They're all the same. You just want to see where does it start, where is one cycle complete, and wherever that is, the time it takes for that one cycle to occur, that's the period of it. Okay? And yeah, keep your mind open to various different types of waves, but if you really think about it, they're all sine waves. They're all sine waves with the Fourier series. Now that goes pretty deep as a subject, but just know that you can make any wave just by adding together sine waves. It's a beautiful fact of the universe. So yeah, the above answer is good, but it doesn't have to be measured in seconds. So typically you'll use seconds to measure the period of the wave, but if you have really slow waves, you might have years or you might have like milliseconds if you have like very fast waves. Like light waves are very, very fast, so they have high frequencies, so they'll have very, very small periods. Like you'll probably have like nanoseconds, but you can use any unit of time that you feel is appropriate for that situation. Okay, cool. So the next question that we got today is, what direction does the Earth rotate? Okay, so let's actually draw out the Earth. All right, it's my favorite planet. I've been there once or twice. Actually, just once, but I've never left. But maybe one day. So suppose that we have the equator here, and maybe if we try to draw some countries or some continents, like we have like Africa down here, Madagascar, here, Italy, boom, like those are the Greek islands, and then it's like the Mediterranean, and then up here, then we have like our countries up there, and then we have like, you know, our British islands here. It's kind of like a yeah, and then maybe over here we can try to draw like this be like Gulf of Mexico, and then a bunch of islands over here on the the Canadian Atlantic area, and then there would be like Hudson's Bay. Quebec's a little taller like that, and then, but you know how it goes, and then you know, the Earth is this crazy place, and the way that it rotates is it rotates. This is the axis of rotation. This is up with right hand rule. Okay, so if you're not familiar with the right hand rule, especially for spinning things, it's like your fingers go in the same direction as the spin. So in this case, if we're looking at the top of the globe, it's going counterclockwise. The direction that your fingers curl in are going to follow the spin, and your thumb is going to tell you the direction of the axis of rotation. So it's going to be up in this case. Another nice thing that we can think about when we are, or a nice thing that you can remember when you're trying to think of which way the Earth spins is, you know, if you ever looked on a map and you see China kind of looks like this, like it kind of has like a chicken type shape, right? It's like this, kind of like a chicken. This would be China. Imagine the chicken walking forward. Okay, so China would be like over here somewhere, and well, China's shape is kind of like this, kind of chicken-like. So you can just imagine that the chicken is walking forward. That's the direction that the Earth is spinning. Another way that you can kind of remember that is, you know, the United States over here. If you're more on this side of the world and more familiar with this geography, you can kind of see it like, you know, Maine is like the head of a turtle, and you know, it's like this is like the turtle's arm or the turtle's leg, and the turtle is like crawling forward. That could be like another way to think about it. Just think about animals and countries that kind of look like animals in terms of the shape of their political borders. Yeah, so yeah, that's cool. It rotates counterclockwise when viewed from the top. Right hand rule pokes you in the face. The China, shaped as a chicken, walks forward. United States looks kind of like a turtle. That's walking forward. Japan is known as the sunrise land in their local languages, and that's because they're the first to see the sunrise. So you can also see, like, you know, they're rotating towards the sun. That could be another way. There are plenty of different ways to memorize this, but my favorite is with the animals. Okay, cool. So yeah, the above solution is good. Many other ways to help remember the direction of rotation as well. Cool. Okay, so the next question that we got on the menu today is, what is a Newton? Units and explanation. So let's just get it started. A Newton, named after Isaac Newton, believe it or not, is a unit of force. Comes from Newton's second law. Oops. Come from second law, Newton's second law. F equals ma. Okay, so this is like one of the most important equations in all of physics, is F equals ma. So this is the force, this is the mass, and that is acceleration. Okay, so we know that newtons is a unit of force. 1 unit or 1 Newton is, let's multiply a mass and an acceleration together to get like a unit of force, to kind of see what properties need to be combined in what way for this to be true. Okay, so we have a mass. Here we have a force. And they're equal to each other when they are multiplied by an acceleration. Okay, let's just copy this and move that down. Another way that we can write acceleration is like this. We can do velocity per time. The change in velocity over time is acceleration. That could be another way to write this out. And we can expand out the velocity into something bigger as well, or something more low level. All right, so just copy this down. And we know that, let's get rid of velocity. We know that velocity is just going to be distance over time. And distance over time per time, that's the same as saying this. Okay, let me find my mouse. Ooh. Let's keep that. And for the distance over time per time, that could be written like this: distance over time squared, right? Because A over B over C is equal to A over B times 1 over C, which is equal to A over BC. Okay, that's just like how that works for like triple decker fractions. And let's substitute these out with, or substitute in SI units. SI stands for Système International. It's a system or an international like science and engineering standard for units. So here we're going to have Newton. I'll write them out in full, and then here we have kilogram for mass. Oops, kilogram. And then here we're going to have meter. And here we have second squared. And to write this out in symbols, we have 1 Newton equals 1 kilogram per meters per second squared. Okay, so that's what a unit is. A unit, that's the units of a Newton. It all came from his Newton's second law. Force equals mass times acceleration. And once we have that, we can derive the units of it just knowing like mass and acceleration, what they are. And we can break down newtons into its base SI components. Okay, so exactly kilogram meters per second, and it comes from F equals ma. Yeah, that's good. So the above solution is good. Is good. Don't use capital K in kg for kilogram. Okay, that's just a minor thing, but still mention it. Okay, cool. So the next question that we got on the menu today is asking us, what are some examples of electromagnetic waves? So electromagnetic waves they are caused by electricity and magnetism. Electricity and magnetism. The reason that they exist is electric waves or electric fields will incite magnetic fields, and magnetic fields incite electric fields. So these fields create each other, and they like chain create each other in like a transverse wave. So they electric fields induce magnetic fields, and vice versa. So let's say if we have red for electric red, and we have magnetic blue, like we're gonna have this and this, we're gonna have this and this, which will incite this. Like I'll just draw these out to like kind of make it like more clear. But like these waves are kind of like this. Kind of what's going on here is, imagine that we have like a line going through here. This would be like a diagonal view, but we know that like vertically this would be like the red, and horizontally it would be the blue. Magnetic, red, electric. So the fields that they induce on each other are perpendicular to each other. It's kind of tough to see from the diagram. And then maybe if we have like a vertical line, like that, but like, just know like the blue is supposed to be horizontal and the red is supposed to be vertical. It's just kind of tough to draw three-dimensional things on a two-dimensional page. But these are kind of what electromagnetic waves are, and they can exist at different frequencies, and at different frequencies they will have different properties. So frequency or wavelength, because they are pretty much the same, they're different ways of saying the same thing. It's like how, you know, how wavy is the wave? I guess is the best way for me to describe that. Frequency or wavelength of wave, of electromagnetic wave, electromagnetic wave determines its properties. Okay, so here, very conveniently, we have a little spectrum of a diagram of different types of magnetic waves and how we can interact with them. So at low frequencies, big wavelength, because they are inversely proportional to each other. So we can write that as frequency is proportional to 1 over wavelength. Okay, they're proportional to each other in an inverse sense. So at smaller frequencies, larger wavelengths will have like radio waves, and these waves are quite long. So if you ever seen like a radio tower, they're transmitting radio waves. That's electromagnetic radiation, electromagnetic waves, at fairly low frequencies, fairly long wavelengths. These could be like a couple of meters. So like, you know, if you spread out your arms, that could be like a wavelength for a radio wave. These are used to like transmit information. So if I have a receiver that interprets those radio waves, you can embed some information inside of the wave to maybe send me a message. Radios do this by sending, like, they encode audio information inside of those waves. So they can do it with amplitude modulation. That's with AM radio versus FM, where they're doing frequency modulation. And how they change the frequency or the amplitude that's how they encode in the information of the sound that you'll typically have when you listen to the radio. That's it's cool stuff. Next thing is microwaves. Microwaves, well, where have we heard microwaves before? Well, I have one in my kitchen that I use to heat up my food when I'm hungry. And the thing about microwaves is that they work because the waves that they produce are at a similar resonant frequency to the resonant frequency of water. So the radio waves, the electromagnetic waves that your microwave makes, will wiggle the water, or they're gonna pierce through your food, but all the water molecules inside of your food are gonna start vibrating at that same frequency, because that's the same as the water molecule's resonant frequency. And because of that, the water molecules are going to increase their kinetic energy, because they're like I mean, the water molecules, to kind of put this in a kind of a metaphor, the water molecules are like, yo, that's my jam, that's my frequency, and they're jamming out. They're like bopping their head to the frequency of the microwave, and as particles increase their kinetic energy and they're wiggling a lot, the temperature increases. So that's why when you put your food in the microwave, it will heat up. But if there's no water in there, there will be nothing to heat up, because it really just goes off the principle of water. Now, the next thing that we got here is infrared waves. That's another type of electromagnetic waves, but the frequency is getting higher, and it's also getting shorter in wavelength. So the waves are more bouncy now, more bounces per a couple seconds of interpreting the wave. Infrared waves are quite interesting because they have a lot of applications. One application is in night vision goggles. So when you're in the dark, you can't see stuff because there's no visible light. But there is infrared light that's always there, because basically, everything still has heat, and heat makes off a lot of infrared radiation. It's kind of like light that's not necessarily visible to our human eyes, but if we have night vision goggles, some animals might be able to see infrared light as well. But night vision goggles, they pick up infrared wave information, and then they transform their infrared information into visible light information, which allows you to see in the dark without flashlight. It just interprets the infrared lights and transforms that into visible waves. And another thing that we use infrared for is for remote controls. So if you ever taken a video of the front of your TV controller as you push some buttons on it, you can see there are some lights that are going to be outside of your TV remote, outside of its light emitter. Those are infrared waves. Some cameras can pick them up. even though the human eye can't. And they're like that because TV remotes are pretty much just laser pointers, but they point infrared light that I guess the receiver, maybe your TV, is going to interpret, and then they'll be like, okay, you just sent me a signal. That signal said, turn myself on. So TV says, okay, I'm turned on, and let's watch a movie or something like that. So yeah, that'd be an example of infrared waves. Next thing is visible light. That's all the light that you can see. It's actually a very small segment of the electromagnetic wave spectrum is visible light. This would be just the light that you see, all of your favorite colors, and like the rainbow, red, green, Roy G. Biv. Like here we have a low frequency, and here we're going to have high frequency. So if you increase your frequency, you're kind of moving more towards the purple side of the rainbow. Yeah, and all colors are just parts of the visible light spectrum, which is a part of the electromagnetic wave spectrum. Okay, cool. So the next thing that we got here is ultraviolet light. And ultraviolet light is light that is a higher frequency than purple or violet, and humans can no longer see it. The sun has a lot of UV radiation, and these waves are much more bouncy, and when you tan, it's really like the UV radiation from the sun that is like impacting the cells in your body, and that's what like causes tanning. And if you have too much, well, it's going to be uncomfortable for you. The next level up in terms of the electromagnetic wave spectrum, we have X-rays. And X-rays, well, if you've ever been to a hospital, I've got an X-ray before when I broke my spine, but it's fun times. X-rays are even higher frequency waves, and they have like much higher energy, and they're used to see through things because the energy in the wave can like pierce through stuff. And even higher level is gamma rays, and these are kind of used for like more like science, but scientific research reasons and that type of stuff. But the higher frequency the stuff is, like these waves have a lot of energy, because the more that you have higher frequencies, the more energy that wave is going to have for it to exist. And these higher frequencies waves, electromagnetic waves, they can do some damage to your body. So that's why typically you don't want to spend too much time around X-rays, because it's not great for you. Also kind of why ultraviolet light, because that comes from the sun. If you're tanning too much, it could lead to some problems with your skin. So yeah, the higher frequency, the more possibility that it can harm you, because the energy will cause the cells in your body to have more energy than they expect, which could lead to some unexpected behavior. And if your cells are not happy, well, you are what you are. You're just made of cells, and if your cells are not happy, well, you could be having a bad time. So yeah, the above solution is good. Could be enhanced with some real world applications of electromagnetic waves. Cool. Okay. So the next question that we got here is, if we have an air core solenoid with 68 turns, that is 8 centimeters long, and has a diameter of 100 or 1.2 centimeters, and when the solenoid carries a current of 770 milliamps, how much energy is stored in its electric field? Okay, so there's a lot to unpack here. First, let's talk about what it means by an air core solenoid. So a solenoid is kind of looks like a spring. Kind of looks like here I have a calendar, and you see like the binding on this calendar. It kind of looks like that, except it's like more in a loop. I would say it's more similar looking to a spring. Do I have a spring? Yeah, I have something like this. So solenoids kind of look like this. They're like, this is just a spring on a grip trainer that I got. So a solenoid is going to look like this. So let's get the brush. Okay, this is what's a solenoid. Okay, and it says we have 68 turns. So 68 turns. One turn would be like, you know, one of these loops. But we got 68 of them. It's quite a few. It's 8 centimeters long and has a diameter of 1.2 centimeters. So its length like this is 8.00 centimeters, which is also equal to 0.0800 meters, just to keep it in like a base SI. And its diameter this way, let's put that in a different color so it's not confusing. In purple here we have the diameter. The diameter is equal to 1.2 centimeters, 1.20 centimeters, which is equal to 0.0120 meters. It's just nice to do some conversions early so that you don't need to worry about them later. Okay, and when the solenoid carries a current of 700 or 0.77 amps, when current I equals 0.770 amps, find energy stored. Okay, so one thing that I want to mention is that this solenoids are inductors. Inductors on your electric circuit diagrams look exactly like this. Like if you had an electric circuit like this, you know, no one would doubt that this is an inductor, which is represented with L. So the potential energy, or the energy stored, inside inductors is modeled with the following equation. We have U. U is typically used to represent potential energy. A nice way is like, you know, potential, pu, potential. Yeah, you know, it got to do what you got to do to remember this stuff. It is 1/2 inductance L multiplied by current squared. You see how it kind of has a similar structure to or the potential energy of an inductor looks similar to like 1/2 mv squared kinetic energy. Also looks similar to spring potential energy. It's very fascinating stuff. That everything looks so similar. But yeah, so we have the I value here because the I is 0.770 amps, but we need to find the L. We need to find the inductance L. Okay, and we have the equation here. Conveniently, it's deeper in the solution. So our the inductance of a solenoid inductance L is equal to let's just use this equation because it would this is just the stuff that we need, because like the other question, well, it does involve like this other constant, but you know, it's not necessarily something that we need to worry about for this. Yeah, so we have L is equal to mu naught, which is a magnetic constant, multiplied by the number of turns squared, multiplied by the area of each turn of the solenoid, all divided by the length of the solenoid. Okay, now we pretty much know all of these except for A. So A is the area of solenoid turn. Okay, but we don't know this directly, but we do know that it is, well, they are circular because these turns are always circular, and they're easier to manufacture when they're perfectly circular. Like, they're not really going to work out if they're squares or any other shape. So the diameter is 0.0120 meters, and if we get the area is equal to pi r squared, and area is just going to be pi times 0.0120 meters over 2 squared. And we can actually just sub that in, and then we can solve for this. Down here is the length. Okay, so here let's sub in our values. So L, we have mu naught. That's just a constant, and this constant is the permeability, not the same as permittivity, permeability of free space. So that is 4 pi times 10 to the negative 7 Tesla meters per amp. Now, we don't really need to worry that much about the units because we know that our inductance value at the end, the unit of that has to be Henry, named after probably some guy named Henry, probably a smart guy. Yeah, so our first one, our mu, is going to be here. It's going to be 4 pi multiplied by 10 to the power of negative 7. Okay, and I'll just write mu above this so we know where all of these are coming from. Now for n, how many turns did we have? The question said that we had 68 turns. So we got 68 squared, and this is number of turns. And then we multiply it by a, which is just pi times 0.012 over 2 squared. So this would be a. And that whole thing divided by the length of it, which is 8 centimeters. So this is 0.08 meters length. Okay, let's send this through the calculator and figure out what this is. Cool. So we got 4 times pi times 10 to the power of negative 7 times 68 squared times pi times 0.006 squared. That whole thing divided by 0.08 meters. And my value for Henry's was quite small. Yeah. So L for me was equal to 8.215 times 10 to the negative 6 Henry. Okay, so this is the inductance of solenoid. Okay, that's awesome. So now that we have the inductance of the solenoid, we can now go back to our original equation. I'll rewrite it down here. U equals 1/2 Li squared. And we can sub in our I and L values to find out the potential energy. So let's do that. 8.215 times 10 to the negative 6 multiplied by, the current was 0.770 squared. And let's calculate it. So take the inductance, multiply it by 0.77 squared, and multiply by 0.5, which is the same as divided by 2. And the answer that I got was hopefully the same as the one they had here. Yep. So U is equal to 2.435 times 10 to the power negative 6 joules. Because energy is measured in joules, and we're using SI units for everything, so we can be fairly confident that we're going to come across joules. And this would be the energy stored inside the solenoid. You could say inductor because this solenoid is an inductor in this case, but I want to use the word solenoid because that's what was first mentioned in the question. And yeah. Now, what does it mean when a solenoid or an inductor is storing energy inside? What basically that means is like if you had this in an electric circuit and you were to suddenly like cut off the current and you just like disconnect all your sources, the inductor would act as a source for just a little bit. All of its stored energy inside would kind of be acting like a new current source, and it would act like that until, of course, it runs out of energy stored inside. So that's kind of how inductors work. They're useful in like AC circuits. Yeah, it's pretty cool stuff. Pretty cool stuff. The above solution is good. Solution is good. Okay, cool. So the next question that we got on the menu today is asking us, what is the law of superposition? There are many different types of situations that you can use the law of superposition, but pretty much the general rule of superposition is that the sum of components is equal to the whole. Okay, let's say that we have, or let's see what examples that we have in here. The superposition as applied for electric fields. Okay, so we can actually see an example of that. So suppose that we have a Q1 here and a Q2 here. And here we have point A. Here we're going to have R1. Distance here we're going to have R2. Now, if we want to find net electric field at point A, use superposition. Okay, so we can actually like empirically write this out as an equation. We know that A is going to experience an electric field effect from both Q1 and Q2. Also, if we had more charges like Q7, 17, 18, 19, up to including up to the 1000s, we could do it the same way. Of course, it would take quite a while. Generally, superposition is going to be easier the less components that you have, but it is always possible. Okay, so if we want to find the net electric field at point A, use superposition. Find E fields from individual sources and add them up. So to set this up as an equation, of course these are vector values. Electric field is a vector. So E net at point A is equal to the electric field caused by Q1, EQ1, plus EQ2. And we know that this is going to be it's going to be something like G, no, not G, KQ over R squared, and this is along R1. Plus K or KQ1 and then KQ2 over R2 along R2. Okay, so this would be an example of how you could do superposition with electric fields and charges. Another way that we can use the law of superposition is in electric circuits. So suppose that you have a situation like this. This is going like quite in depth. So suppose we have a source like this, and we have a current source, and then we have another voltage source. We call that VS1, IS, and then VS2, and this can be R. And if we're trying to find the I going down R, what we could do is we could use superposition and look at these sources in the circuit and look at the sources individually, add up all of their contributions, and that would be that. So you would use something like this. So VS1 individually, alone. You would zero out all the other sources. What I mean by zero out, so this would be VS1. R stays the same. Current sources become holes, or they become disconnected, so it's open. And this would be zeroed. So this would be a short. And this would be like I VS1. And then the next thing that you would do is IS alone, and you would zero out those voltage sources, still have R, you have the current source, and then just that, and then you would get your I from IS, and then you would do something like VS2 alone, and you would have that would be a short circuit. This would be R, this would be I. Oh, whoops, that wouldn't be included. That current source would be cut out. And then plus minus VS2. And then this would be I VS2. And then your actual I would be something like I equals I VS1 plus I IS plus I VS2. Okay, so as you can see, the law of superposition can be applied for many different things. When you're doing circuits, it's a perfectly valid way of trying to solve a circuit. When you have multiple charges and you're trying to find the net electric field, you can do it with superposition. Another thing that you can do with superposition is with waves and the superposition of waves, sometimes to see how they interact. So initially I'll just show this. So here we just have a red sine wave. The red sine wave, fairly straightforward, nothing too fancy about it. And then we have a slightly phase offsetted another sine wave, but it's got a little slight phase offset. Okay, so if we wanted to get like this wave, this green wave would be their superposition, and at every single point at this wave, it will have the value of the red plus the blue. So here at this little line here, we have 0.84 plus 0.909. We should expect maybe a 1.75 or so. Yeah, exactly. So them added together is precisely what we expect up here. And you see at this point here, the red is 0, so they should be the green and blue should be perfectly aligned here. So this just goes to show like superposition is just adding up the components, and you will get the whole if you just add up the components. Okay, cool. So yeah, the above solution is good. Is good. Answer could be enhanced with some other situations where the law of superposition be used, such as with waves and electric circuits. Also, net gravitation, perhaps. This could be another example. But net gravitation will be very similar to what we already see with electric fields here. Okay, cool. Okay, so the next question that we got on the menu today is asking us, what is the unit for acceleration? Okay, now acceleration, as we know, is related to velocity, which is related to position, and they're related through calculus. So if we have position, or I'll first define our variables. So we have position x of t, and we have velocity v of t, and acceleration a of t. Now, why I write them all as as functions with respect to t, because we'll need them to be functions with respect to t for them to be related at all, and you can't necessarily guarantee that any one of these three things are going to be the same at different points in time. Like my position right now could be at position 0, but I take a step back and position or time equals 1 second. I'm 1 step backwards, so the x value is going to be different. So if we want to get v of t, v of t, we take the derivative, the time-based derivative of the position. And a of t, we take the time-based derivative of the velocity, which is just the double derivative, so the time-based derivative of the time-based derivative of x of t. Okay, so the units for x of t, this is just going to be a length. Okay, when we differentiate length with respect to time, differentiating means that the unit is going to be divided by what we're differentiating with respect to, in this case time. So this is going to be length over time. And acceleration, we're just doing, since it's the derivative, the second derivative of position, will be length over time over time. Time over time, which is equal to length over time squared. Why does that work out? Well, suppose we have a over b over c. This is equal to a over b multiplied by 1 over c, which is equal to a over bc. Okay, that's just how the units work out. Just by knowing this little rule about fractions, dividing is the same as multiplying by the reciprocal, and it looks fairly straightforward based on that. Okay, but it also depends on like which division you do first, but typically you want to go top to bottom, which is what we've done here. Okay, so cool. So we know that the units for acceleration have to have the properties. Acceleration, it has to have the properties length over time squared. So if we use SI units, the length is measured in meters. So m per second squared. If we are USA units, we might have feet per second squared. Because I guess it's a good thing that we use the same time units all across the world. I'm very glad that we are not using we don't need to do a unit convergence for time. That would be uncomfortable. But these are just some examples. Example units. You can really sub in whatever you want for length and whatever you want for time. If you really want to, it could be acceleration, could also be, let's call them custom units. It could be maybe, a football field. Per year squared. It doesn't matter exactly what you put in for your units. Of course, this is kind of a ridiculous unit, a football field per year squared. But that, as long as you have a length over time squared, some unit of time, doesn't have to be seconds, it could be years, it could be whatever time you want, that will give you the units of acceleration. Okay. But typically the most common one that you'll see is meters per second squared, because SI stands for Système International, international system of standardized scientific units and properties that hopefully everyone is able to use, so that it's easier to collaborate with our peers. Because if everyone was using custom units like this, and I'm saying oh, I'm accelerating one football field per year squared, other people I'm trying to collaborate with, they're like, what do you just say? What type of unit is that? How are we going to convert that to something that we can all agree on? So that's why it's good to use SI units, because most countries in the world, aside from 3, use these units a lot. Okay, so the above solution is good. Solution is good. Should mention that it's just a length over time squared, and that any units for length and time can be used. SI units are very commonly used, but are not the only possible units for acceleration. Okay, cool. Okay, so next question that we got on the menu today is, how can we determine the wavelength of a wave, presumably of a wave? A wavelength has to have a wave that it occupies. How do we calculate the wavelength of something given its energy? And the equation that we want to use is this: energy is equal to H multiplied by F. So I know here it might look like it's a V. I think it might be possible that some people use a V looking thing to represent frequency. I guess since I've seen that so many times, I can kind of understand it, but I would highly recommend that you use F to represent frequency instead of V, because F starts with the first letter of frequency is F, so that makes sense there, and it will not be confused with velocity or anything like that, because this, I don't even know if that's actually supposed to be a V or if it's just a Greek letter that looks like V. I could easily be confused for velocity, and we do not want that. I would recommend using F instead. But this is the equation that we're going to use. E is going to be the energy. H, this is Planck's constant, or Planck. It was named after Max Planck. He was a very famous scientist. I actually have a picture of him on my wall over there at the Slovak conference, one of the conference of some of the top tier physics back in the early 1900s. Yeah, so that's his constant that we're going to use. And here we have frequency. Okay, so this is the energy of a photon. Which is, and photons are kind of like waves, kind of like particles. That's a controversial statement to say that a photon is either a wave or a particle. It's kind of controversial. So is it a wave or a particle? Yes, that's what it is. It's got properties of both. And we know, well, we have frequency, but what we really want is our wavelength. And we know that with the universal wave equation, we have the velocity of the wave is equal to f times lambda. You can see why we don't necessarily want to use that v looking thing for frequency because of this equation, and it'll be quite confusing to have two v-shaped things. If we want to solve for the frequency, it would just be v over lambda is equal to frequency. So we can sub that into here, and we'll have energy is equal to h v over lambda. And it's asking us, how do we calculate the wavelength given energy? So we're trying to isolate the wavelength here. So let's send it to the other side by we can multiply both sides by wavelength, divide both sides by energy. So the E is going downstairs on the right hand side, and the lambda is going upstairs on the left. The E and the lambda are really just switching positions like that. So we have H over V over E. Okay, now let's get some values. So in this case, H is equal to 6.626 times 10 to the negative 34, and that's just the constant of Planck's that we're using. V is the velocity of the wave. Equals V equals C in this case. And C is the speed of light, which is 3.00 times 10 to the power of 8 meters per second. And then once we have our energy, well, it doesn't specify what energy that we should use, but we can get like a more simple version of this. So we can get lambda is equal to 6.626 times 10 to the negative 34. Multiply that with 3 times 10 to the 8, and all of this divided by energy, so we can get a nice like a one number relationship for this. Okay, so setting that in our calculator, Planck's constant times the speed of light, 6.626 times 10 to the power of negative 34. Multiply that whole thing by 3 times 10 to the power 8, and we get lambda equals 1.9878 times 10 to the negative 25 over the energy, and that will give us the wavelength. So if you have an energy value, let's say your energy is 1 joule, your wavelength would be 1.9878 times 10 to the negative 25 meters. Okay, so yeah, this would be your equation given this, and HC over E, yep, that's exactly what it is. And here is just like H and C multiplied together, gotten as a single number. So if you're using this function a lot, it would be easier to use this. Okay, cool. The above solution is good. Might be better if the subbing in of H and C was shown. Yeah, cool. Okay, so the next question that we got on the menu today is asking us, what is the principle of the superposition of waves? So the superposition of waves, let me write that out. When waves intersect, the result is that the individual components added together is what's going to be the final wave of when waves intersect. When waves intersect, the sum of the components will be equal to the resultant wave. Okay, now what does that actually let's actually use like a visual example to see what's going on. I have a similar model here on Desmos, just a classic graphing calculator. Okay, so I'll first hide these. So suppose that we have this red sine wave, just a regular old red sine wave, and we have a blue sine wave that's like intersecting with it. So they're both going at the same time. Okay, now what the superposition theorem says for superposition of waves is that the superposition of these two waves intersecting at this point is just going to be them added together. So you can see from the green wave here, the equation is defined as exactly the red plus blue. And here, let's zoom in a little bit. We can actually close that, just get a bit more space. We can see that, okay, the value of the point here, that's green, is 1 is equal to 1.7508. We should see that this should be precisely the same as the value of the blue at this point, which is 0.909, plus the value of the red at this point. And if we do some quick math in our head, we can see that, hey, 0.8415 plus 0.9093, that has to be precisely the same as this. So that's just showing, like, at this point, the superposition theorem, what you would do, you would just find the values of the individuals, add them together, and you'll get the resultant value. Okay, now if you see here, at this point right here, you see the red is 0. So you would expect that the green and the blue are precisely the same at this point, which is 0.8415. So yeah, that's pretty cool. Pretty cool. Let's say if we moved our thing along to like here, even in the negatives, it's still the same. Maybe over here it's going to be a little like that. So over here we have like negative 0.38, pretty much negative 3.9, negative 9.8. So we should expect maybe just under negative 1.3, 1.4, negative 1.4. That looks about right for what these two values added together would be. Or negative 1.37. Okay, so even when they're negative, you just add them together. You see here is a case where we have one that's positive and one that's negative. So yeah, you just add them together, or subtract the negative one from the positive one. But that's the same as just adding them together and including the signs. So superposition of waves, wherever they intersect, the sum of the components is equal to the resultant. Okay, so yeah. The above solution is good. Is good. Might be better to show an example with a square wave as the sum of the components might be more obvious. Okay, cool. Oh man. Oh man. That was our last question. Ain't that unfortunate? Time flies when you're having fun, as the old saying goes. I always have fun doing physics. So, those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button below and ring the notification bell if you're very eager on never missing another one of our OneClass uploads. If you would be interested in submitting your own questions, check out the links in the description below. Remember to leave a like if you like the video and comment your thoughts on it. Share the video with your friends if you really like the video. And this has been Millan with OneClass. I hope to see you again soon. Take care and have fun being a physics champion. Remember, physics will never betray you. Physics is fun. Physics is freedom. Anyways, take care, all of you physics champions. Take care.